In early spring of 2026, two massive, interconnected federal policy shifts arrived simultaneously, permanently restructuring the Canadian AI sector. The first was the launch of the $705 million AI Sovereign Compute Infrastructure Program, or AISCIP. This is a deployment of capital aimed at building a publicly owned, domestically controlled supercomputing testbed for the country. The second shift came from the Canadian Intellectual Property Office, which released its pivotal March 2026 practice notice. This document establishes a specific legal redefinition of patentable subject matter for computer-implemented inventions. On the surface, these events look disconnected. One is a massive infrastructure project. The other is dense administrative legal guidance. These two federal vectors share a singular, uncompromising engineering mandate for Canadian AI companies. This mandate is physicality. AI innovation in Canada can no longer exist as pure theoretical software. To secure federal infrastructure funding or intellectual property protection, machine learning models must now be anchored to hardware or prove a measurable computational efficiency. Mastering the convergence of physical infrastructure and intellectual property law has become the baseline requirement for the Canadian AI sector. We can deconstruct the $705 million AI SICP ecosystem to see how this hardware strategy actually functions. The program targets a specific vulnerability: Canada's reliance on foreign cloud infrastructure to process AI workloads. ISED's solution is a sovereign architecture divided into two distinct, integrated layers. The first tier is the infrastructure build layer, including physical components like modular data centers and AI-optimized supercomputers. The second tier, the national service layer, manages user support, training, and data services. These layers must integrate to provide a functional testbed for Canadian innovators. This architecture ensures that data residency and operational control remain strictly within Canada's borders. By creating this environment, domestic technologies can scale up without leaking intellectual property to foreign supply chains. But building physical infrastructure is only effective if the innovations generated on it can be legally protected. Software and models trained on this hardware must still survive CIPO's new stringent legal requirements. CIPO's March 2026 practice notice was a direct response to the federal court's ruling in Dusome v. Canada. To evaluate tech patents, CIPO adopted a specific interpretation phase called purposive construction. Under this phase, examiners must determine what an inventor actually invented before testing for patentability. This creates a specific decision flowchart. The first test asks if there is physicality outside the computer. If the claim includes external physicality, like a real-world sensor measuring data, the requirement is met. If the model exists entirely within the computer, the analysis shifts to the Schornberger question. This stems from a 1981 decision that rejected a patent for being a mere mathematical calculation carried out on a machine. That 1981 legal rule is now the primary filter for 2026 machine learning patents in Canada. The test asks if the invention simply processes an abstract algorithm in a well-known manner. The only acceptable bypass is to prove that the invention provides something more by meaningfully improving the computer's internal functioning. Software patent claims must now prove they are fundamentally upgrading the physical performance of the hardware. Under the 2026 rules, accurate AI models cannot be protected unless they can prove they alter the physical operation of the machine running them. We can apply the Schlumberger framework directly to modern artificial intelligence. CIPO legally treats a highly complex, trained neural network as an abstract algorithm. CIPO's Example 3 describes a neural network trained to generate a crop irrigation schedule. CIPO rejected this because generating an optimized prediction is considered providing advice, which lacks the required physicality. To cross the physicality threshold, claims must follow one of two pathways. Pathway 1 is external physicality. The AI's output directly triggers hardware, like an irrigation valve. Pathway 2 is internal computational improvement. The model optimizes the computer itself, like reducing memory load. This requires patent specifications to describe architecture in computational terms, like reduced memory load or faster inference speeds. AI patent eligibility in Canada is no longer measured by a model's intelligence, but by the physical efficiency it brings to the hardware. Infrastructure funding and IP protection have converged into a single strategy for Canadian AI. The AI SCIP provides the sovereign physical hardware required to train next-generation models. CPIO requires that the intellectual property generated on that hardware proves measurable efficiency improvements. The IP legal layer now depends on the hardware layer's operational metrics to exist. Claims focused on abstract AI outputs no longer meet the threshold for Canadian protection. Whether an organization is securing deployment under the AI SCIP or prosecuting a patent at CPIO, the mandate is the same. Long-term strategic success now requires a provable connection to physical computational reality. In 2026, Canada's AI advantage belongs to the firms that master the integration of software with sovereign physical compute.